In this video, my focus will be to explain what are the parameters of this method model.compile and this method model.fit. So let me quickly review what we would like to do in case of building an AI model or a neural network model. Say we have an input variable that looks like this, which has values 72, 66, 64, and so on. And then let's say here's our output variable whose values look like 50, 31, 32, and so on. In other words, in case in this example, if this was blood pressure, and if this was age, then what we would like to do is build a magical thing known as model that takes blood pressure as input and that can predict age as output, right? So this is our AI model that does the magic, that is takes blood pressure as input and predicts age as the output. So this model basically is some complex mathematical function. And in the case of univariate linear regression, this turns out to be something extremely simple. So in this case, this model is actually nothing but a mathematical equation where we say age equals blood pressure times a constant weight plus a bias. So here's one network parameter, another network parameter, or the model parameter. But then basically this model is nothing but this mathematical function where it simply takes the blood pressure as input, multiplies the blood pressure with a weight, adds a bias to it, and produces the output age. So this is how the model makes predictions basically. And then the way we can make the evaluation of the model is by comparing how good the predicted age is against the true age when we actually have the true age at our hand. So to build such a model where we create this model and automatically learn the weights and the bias parameters, this is how TensorFlow can help us. The first thing we do is we import the libraries. In particular, for this case, we need two libraries. One is the sequential class in the models library from Keras and the dense layer from the layers. Now, what this sequential class does is allows us to build an empty model that's of type sequential. Now, why sequential, and are there other kinds as well? The answer is yes, there are other kinds as well. Sequential is the type of model where if you have your input, then the neurons or mathematical operations that take place inside the model are always in like a sequential process. Your input goes in and they sequentially go all the way to the output for the output to be produced. So the other kinds of models could be recurrent architectures where your neurons could be connected such that there are connections within themselves, there are cross connections, and other kinds of connections where your input does not necessarily go from, say in this case, all the way from left to the right. There could be cross connections and other kinds of connections. So those are non-sequential models. So the first thing we do is create an empty model that's of type sequential. The next thing we do is add a dense layer. So once we create a platform, an empty place for a model for us to keep adding layers, the first thing we do is add a layer called dense. Now this word dense stands for a special type of network, and this network is something known as the feed forward neural network, feed forward neural network. What this basically means is neurons connected in a feed forward fashion. This is your input, the output from previous layer goes to the next layer, and from the next layer to the next layer, and then to the output. Now, in the dense layer, the parameters that we are specifying is 1. So this 1 basically means that we have only one neuron as our input. So one neuron means we have this neuron, and it receives inputs. Here, the parameter input dim equals 1 specifies that the number of inputs this neuron is going to receive is only 1. And this is the case because our input is only a single variable, one column input. So this this model only receives, this dense layer only receives single input. In this case, the input is BP. We know that by definition of a neuron, or the way linear regression works, the input BP is going to be multiplied by a weight, and a bias will be added to this weight, and then what comes out is predicted as the output. Now, this parameter activation equals linear implies that no further activations are applied to this output. So this output that we have, BP times weight plus bias, typically in a big neural network, what happens is this output goes as input to another function. Typically, it's either a sigmoid function or some other kind of activation. In other words, what this sigmoid function would do is take this as input and produce a number between 0 to 1. So these activations are like, functions that take your model's some output, some input, and produce an output are absent here. So linear simply means we don't do anything. We simply multiply the blood pressure with the weight that the model has to learn and the bias that also the model has to learn, and then simply produce the output without making it go through any sort of activation function. So up to this point, what we have done is we have built a model. We have built a model. And then the next thing we do is we do model.compile. This process is to specify the loss, optimizer, give some metrics if we want, and also to check for errors if we have accidentally made connections that are not allowed in a sequential model. So this basically checks for the syntax errors in our process, or even logical errors that we had in the process of building a model. Now, the first parameter for calling the model.compile function is the loss. So what this loss equals MSE here stands for is MSE is mean squared error. So here, mean squared error simply means as we build the model, we are going to pass the model the true output values as well, so that the model knows how bad the weights are, and then it can update it, right? So say, for example, we have this model, and then we pass blood pressure as input, and let the model randomly initialize weights and bias to certain values, and then also make predictions from the model. Let's say we predict A's, B A's. So then we also need to supply these values, which are P true for the model, to calculate the loss, to calculate the error, so that the model knows how bad its predictions are. And there are different ways we could calculate this loss. So this difference between the prediction and the true is the loss, the error. And one way to calculate this is to simply calculate the difference, that is absolute difference between prediction and true values. Another way to calculate this is to calculate the square of this error. And this is exactly what mean squared error means. So if this error is calculated between multiple examples, then this simply becomes mean squared error. Now with loss equals to mean squared error, what we are telling the model to do is, well, you may have initialized weights and biases to certain values, but then when you calculate the loss between your prediction and the true values, always use mean squared error. And with these values that you get from the mean squared error, learn to update these weights. So this is going to give feedback to the model to update its weights and biases, so that in the future, the model makes better predictions. And this is an iterative process. Now, this parameter optimizer equals RMS prop is the algorithm that your model uses to iteratively update the weights. So the way weight updates work, or specifically in the case of neural networks, back propagation algorithm works is your model takes certain blood pressure as input, makes predictions, calculates the loss, updates the weight and bias values, and then makes predictions for remaining data or for subsequent data, again predicts the output, again calculates the loss, again updates the weights, and then goes back, makes further predictions, and continues the cycle. So this cycle of taking the input, making predictions, calculating the loss, updating the weights, and making predictions using the weights that are updated is a iterative cycle, and it does and the model, we would like the model to do this continuously until no further weights and biases can be updated to get lesser and lesser loss, right? So this back propagation algorithm, the process of updating weights is controlled by your optimizer. There are various kinds of optimizers. RMS prop is one of them. There's Adam, there's NADM, there's a SGD, there's gradient descent, and so on. So RMS prop, usually there are around a dozen or so these kinds of optimizers, and RMS prop usually pretty much works for most problems, at least at the beginning when we are learning machine learning. Now this parameter matrix is simply informing the model.compile that as you perform these weight updates, and then every time you do these weight updates, you might want to report us how bad the predictions are. So MAE is simply the absolute difference between the predictions and the true. So this is mean absolute error. So MAE is simply calculating the difference between the true that we have and the prediction that we have. Now with matrix equals to MAE, what this model is going to know is in future, as it reports its performance during the process of learning, it's going to simply calculate MAE and report that to us. Now the last function, model.fit, has a lot of parameters as input too. The first parameter that we supply as input is the X, that is the input to the model. So this is where we specify, take this column that we have as input. So this is all rows, the first column. And the second parameter is the Y for our model, that is the actual labels that we want to provide the model. So these actual labels will provide the model so that the model can calculate the error during the time of learning. Later, when we actually use the model to make predictions, we don't supply Y, because at the time of making predictions, we don't know the true value. So this Y is supplied to the model only during the training, that is when we call the model.fit process. Now the next parameter we have is epochs. So this epochs is the number of times we want the model to see the entire data set, In other words, if we have epoch equals 5,000, that means during the process of doing these weight updates, that is updating the weights and building the model, our model sees the entire set of data 5,000 times. Now, even in one epoch, even within a single epoch, in one epoch, the model might split the data. So if I have 1,000 rows of data, the model may look at 32 examples at a time. So look at 32 examples, update the weights, and then go back, pick up the next 32 examples, update the weights, and go back and pick next 32 examples, and so on until it has scanned through the entire data set. So this all happens in a single epoch. So in one epoch, the model looks through the entire examples at one time. And this parameter is known as batch size, and we can specify batch size when calling model.fit by simply putting batch underscore size equals whatever number we want as an additional parameter in the model.fit function. So I think by default it's 32, but we can specify smaller number of values of batches when calling the model.fit function. Now, larger batch sizes may make your training run faster, and smaller batch sizes may make your training go slower, but then usually leaving it to numbers like 16, 32 works very well. The last parameter, verbose equals 1, is simply telling the model whether or not we want the intermediate outputs to be shown in the screen as we run the model.fit. The options are 0, 1, and 2, depending upon how verbose we want. For example, if we specify verbose equals 0, then this right here does not have a lot of meaning because we will not be able to see the MAE while the training is happening.